Okay, just to keep up, we're now at section 2.5 acceleration. I kind of joined the three sections 2.2, 2.3, and 2.4 all together on the last video. So we're starting at 2.5, and we're going to include 2.6 on this uh, in this one. And let's share this screen, and we're going to be talking about acceleration. So if we look at the diagram, we see that a car moves with different velocities at points A and B. And we experience it all the time. You're at a stoplight, the light turns green, you're at 0 meters per second when you start, and then all of a sudden you're at 5 meters per second at point B. So a car moves with different velocities at point A and B. The slope of the green line is the instantaneous acceleration of the car at point B. You could also get the slope of the line at point A. You would get a different velocity. Notice that the slope is negative, so it's actually slowing down. The peak of it is right. I don't know if you can see my. Let's go back. If you can see my cursor right there at the peak, the top of that, I would call it a brownish red line. That's the peak velocity. That's the highest velocity. So the slope of the green line is the instantaneous acceleration of the car, and the slope of the blue line connecting A and B is the average acceleration of the car during the time interval from from delta t equal t final minus t initial. So the average velocity is delta Vx, that's velocity in the x direction, over delta t. So that's v in the x direction final minus v in the x direction initial divided by t final minus t initial. That's the average velocity. That's the blue line. Now the instantaneous acceleration is the limit. The instantaneous acceleration is the limit as delta t approaches 0 of delta Vx over delta t, which is it's the derivative of the Vx line, of the Vx equation, dvx dt. So the acceleration at any time equals the slope of the line tangent to the curve of Vx versus t at any time. So if you look, the acceleration, the car, let's say this is a car, you can see that initially it starts off and it's going up the slope at TA. That's probably its peak, and that you can see that below TA on the acceleration line is the top. But you notice as you cross TA on the upper graph how it starts bending over. So the car is actually slowing down, and at some point it's slowing down. It's still going positive, but then it starts going in the negative direction. The velocity starts going backwards. The slope is downwards, and so the acceleration at that right there at the top is 0 as it starts backing up. I mean, you can also think of when you throw a ball up, the velocity decreases, and when it reaches the top of the apex, it's 0, and then decreases in the negative direction. And so you can align this acceleration graph with the velocity graph, and see how it reacts. Okay, let's do a quick quiz. Make a velocity versus time graph for the car in the figure. Suppose the speed limit for the road on which the car is driving is 30 kilometers per hour. True or false, the car exceeds the speed limit at some time within the interval 0 to 50 seconds. Well, I don't think I'm going to wait for you to make a graph, the answer is false. If you were to make a graph, you would see that um, it actually drops down at going a little like I'm going to say 4.6 meters per second, and it drops down from there. Okay, force and acceleration. The force of an object, and we're going to get to this when we get to Newton's laws of motion. The force of an object is proportional to the acceleration of the object. So, oops, wrong one. So the force is proportional to, the force in the x direction is proportional to the acceleration in the x direction. And for those of you that have had physics before, you know that the force equals, not as proportional to, but the force equals mass times the acceleration. But right, we're not there yet, so here it just gives you that the force is proportional to the acceleration. Now, if a car is traveling eastward and slowing down, what is the direction of the force on the car that causes it to slow down? So if it's traveling eastward, I'm just picking east in this direction. If it's slowing down, then the acceleration is in the opposite direction. If a car is going this direction and it's speeding up, then the acceleration is in the same direction. But if it's slowing down, the acceleration is in the opposite direction. We'll study that more when we get to motion diagrams. So if a car is traveling eastward and slowing down, what is the direction of the force on the car that causes it to slow down? Is it eastward, westward, or neither eastward or westward? And the answer in this case is westward, B. In other words, if it's slowing down, it's in the opposite direction. Okay, acceleration. The acceleration is the derivative of the velocity. So acceleration is dvx over dt. But what is velocity? Well, velocity is the derivative of position over time. So it ends up being, acceleration is the second derivative, d squared x over dt squared. It's the second derivative of position. So the acceleration is the first derivative of velocity, and it's the second derivative of the position. Okay, and motion diagrams. This is actually the next section. This is 2.6, but I think it's instructive to talk about it here. We can see in the top A, it's a car moving with constant velocity, and you see each of the red arrows is the same size, and you can see the spacing between the cars is uniform. So this is a car moving in constant velocity, at constant velocity. That is zero acceleration. And B, this car has a constant acceleration in the direction of its velocity. So if you can see in B there, the middle diagram, the acceleration is constant. All those little purple arrows, they're all the same. But notice the red arrows, they increase with time. And not only that, the spacing between the cars increases because it's speeding up. Now let's look at the third one. This car has a constant acceleration in the direction opposite its velocity. Now notice the red arrows. They're all pointing in the same direction, but they're decreasing. The car is slowing down. Each subsequent red arrow is smaller than the one preceding it. Notice the purple acceleration arrows. They're all the same size. Those little purple arrows at the bottom, they're all the same size. Also, notice the spacing between the cars. The spacing is getting closer and closer because as time goes on, it's slowing down. So it's not covering as much its position. It's not covering as much distance as the one where I want, I guess, that it's not covering as much distance for the same time interval. And I think we have a little quiz. Which one of the following statements is true? If a car is traveling eastward, its acceleration must be eastward. Well, we don't know whether it's speeding up or slowing down, so we can't say anything about that one. If a car is slowing down, its acceleration must be negative. Well, if it's slowing down, then the acceleration has to be opposite the velocity. So that seems like a plausible answer. Let's look at the third one. A particle with constant acceleration can never stop and stay stopped. Well, I don't think that's true. We're going to have to learn a little bit about acceleration, and I'll say that I'll talk about it after we. With constant acceleration can never stop and stay stopped. You know what? I was gonna say it's B, but it depends on your definition. So if a car is traveling, you can say that if a car is slowing down, its acceleration is opposite its direction. But what if the car were traveling in a negative direction? Then its acceleration would be positive. Um, so I think that one is a little ambiguous. I'm going to go with C. A particle with constant acceleration can never stop and stay stopped. And that's the one, because there's an important point about constant acceleration that we need to learn. If I have, let's just take my phone and if I just set it down here on the tabletop, it's got zero acceleration. It's also got zero velocity. So it has constant acceleration. Zero acceleration is constant acceleration. So to say that it can never stop, that's not the case. I mean, it has an acceleration. If I put it on the table, it has a constant acceleration. The acceleration is gravitational acceleration, 9.8 meters per second squared. There is acceleration present. That's what keeps us gravitationally downward on the Earth. We're all experience gravitational acceleration, so we have constant acceleration all the time. Okay, and I think that's it. The next, so we're going to do particles under constant acceleration, but we'll save that for next time.